Okay, guys. So by now, I hope you guys refresh why you have to know how to write structures like Lewis structures, to see a three-dimensional description of a molecule. Just to make sure, remember, carbon only has 4 bonds traditionally, covalent bonds. Hydrogen has 1 covalent bond. Oxygen has 2 covalent bonds and 2 lone pairs of electrons. Nitrogen has 3 covalent bonds and 1 lone pair of electrons. Okay, so based on this, you now must always look for this type of bonding in regular molecules. Of course, there's gonna be exceptions, and I'm sure that you saw when this carbon is missing 2 electrons and when it's just having the electrons without bonding to anything else. That's going to be important because we're going to have carbocations or carboanions, the same as we did for salts in the general chemistry process. Now, after that, you also have to know why do we have these types of representations in which the carbon, which it has 4 bonds, but it's not in a flat way, in a monodimensional structure. It is in a 3-dimensional structure. So the best way to distribute 4 centers around carbon is by having this shape, which is a tetrahedron. Hydrogen is very easy. It's just 1 covalent bond, no problem there. For oxygen, we're going to have 2 covalent bonds in an angle because these pairs of electrons are repelling each other, and they are repelling strongly. So they are closing that gap between the covalent bonds. In the case of nitrogen, we're going to have 3 covalent bonds distributed equally in a 3-dimensional plane, and it's going to give me exactly the same shape as I have for carbon, which is a tetrahedron, but I'm not going to be able to see the lone pairs of electrons. So if I just look at the nitrogen in that type of molecule, I'm going to see it like a pyramid, like a trigonal pyramid. But the angle between the bonds is going to be 109, the same as you have for carbon-containing groups. So with this knowledge in mind, if you get like a condensed formula such as this one, C3H8, you will be able to tell the Lewis structure because each carbon is going to have 4 bonds attached to it, to each one of them. So in each bond, you're just going to plug in the hydrogens. And this is what is known as the skeleton of a molecule. The skeleton representation, in which you are clearly indicating where is each atom. The next molecule that I have 2 nitrogens and 4, it should have 4 hydrogens. I have that my representation, my Lewis structure is telling me that I'm going to have in each nitrogen 3 bonds, and each nitrogen is going to have 1 lone pair of electrons. So the rest are going to be hydrogens. Things to remember: these carbons are not flat. They have a shape which is tetrahedral. So if we look at them in a 3-dimensional space, I'm going to see like a zigzag line. And that's where it's going to show me the next type of representation, which is just the line structure, in which I have each vertex or each end of the line is representing a carbon atom. Usually you don't represent hydrogens in these types of representation for molecules. Okay, this is a zigzag representation, and it's implicit that each vertex or each end of the line is describing a tetrahedron carbon atom. Some things that you also have to get from this portion of the chapter is that single bonds are called or come from a hybridization called sp3, and they are all called sigma bonds. So when you mix two things, that's when you get a hybrid. So basically you're mixing one orbital s with three orbitals p to make the best energetically possible bond in which the energy is distributed equally. So that's the whole purpose for you to review that session, that section, because you need to understand why is this happening. It's because the energy is optimized this way to have four equally strong bonds in each carbon atom. If you have double bonds in a molecule, you're gonna have what it's a hybridization called sp2, and the second bond is going to be called pi. So sp2, I'm combining one orbital s with two orbitals p, and I'm getting an extra bond, which is called pi bond. Pi bond. Triple bonds. Triple bonds come from mixing one orbital s with one orbital p. And that means that I'm gonna have two extra pi bonds. And that's because we want the energy distributed the most efficient way possible. So if you ever see carbon, double bond carbon, you know that each carbon is gonna have 4 bonds total. So I need to complete the 4 bonds. Each single bond is gonna be a sigma bond, but each extra bond that you have in between centers is going to be a pi bond. So all these are sigma bonds. The extra one is going to be pi bond. So this is just to support the material that you read and make sure that you understand.